continue today's lecture with point location algorithm that we started with last time. And to recap, the idea that we were pursuing is that you start with a planar subdivision, and we identified the following problem, that how do you find out a large independent set. Okay. So let me just write the algorithm again. So algorithm for pre-processing a planar subdivision. So, one, find a fractional independent set. Okay. So, this word fractional independent set means that an independent set of vertices that has size greater than or equal to, let us say, alpha n for some constant alpha. Okay. So, how do we find this thing? So, we noticed that we had observed that there are at least n over 2 vertices in a planar graph that have degrees less than or equal to 12. That followed from the Euler's formula, right. So, we have a fairly large number of vertices which are bounded degree, bounded by this number 12, right. So, what we do is we just find, so now select vertices from find a fractional independent set, call it F. Okay. So, I am calling this as F. I am denoting this as F, the set of vertices that okay, yeah. So, you want to construct this set F, okay, and we had observed that there are at least n over 2 vertices in a planar graph that have degrees less than or equal to 12, denoted by, say, denote by let us say V prime. Okay. Now, select vertices from V prime such that if we choose a vertex V in V prime, okay, we exclude all the neighbors. Okay. So, we have some vertex V, okay. We have a number of neighbors of this vertex, but we know that there are no more than 12 neighbors, right. So, no more than 12 neighbors, the neighborhood of V is less than 12, and if we choose V, if we select V in the set in the fractional independent set, if we choose a vertex V to V prime, we exclude all the neighbors of V which means that any other neighbor cannot be in the independent set by definition, right. So, that is what we do. And so, if you just do this in a greedy fashion, okay, you start with an arbitrary vertex with that is degree less than 12, okay, and continue with this process, keep adding this to f. Okay. So, build f this way. So, if you build f in this greedy fashion, it is guaranteed that size of f will be greater than or equal to. So, if we choose a vertex, we are certainly we are excluding at most 12 vertices, right. So, and we are working on half the number of vertices anyway, right. So, this means about okay. So, just to be safe, I am just saying that this is, let us say, v over 25. So, alpha is 1 over 25 for sure. So, some fraction. Now, it is actually a very small fraction, and that will show up in the final constants. Okay. So, if you can get a better bound by some with a more tight argument, maybe this 25 can improve to 20 or something like that. Okay. But you can't improve it too much, because it is a fairly naive and simple approach of computing the fractional independent set. Okay. The next step is so after having done this, okay, so step 2 is exclude or delete f from the graph. Okay. So, initially that is called the graph g equal to g 0, let us say, okay, v 0 f 0. So, exclude these vertices from the graph, okay, resulting in a modified graph, right, call it g 1 of v 1 f 1, okay, where v 1 is basically the initial set of vertices minus not sorry, we should call it E 0, right, E 0 E 1 v 0 minus f. Okay. So, we have thrown away those vertices. Okay. So, exclude these and then repeat step 1. That is, we again find a fractional independent set. Notice that G 1 is also a planar graph, right. You are only throwing away vertices and edges. So, if a graph was planar initially, it must remain planar, right. Also planar and similar arguments apply. Okay. That is, we can again pick a fractional set using the same argument and the same procedure, okay, and you keep repeating this. So, what is happening? We started with some graph G 0, okay, and then we threw away some vertices resulting in graph G 1, okay. Then we threw away some more vertices resulting in graph G 2, okay, and we continue. How long can we continue this process? Okay, every time we are throwing away out a constant fraction of the vertices, right. So, how many times can we repeat this process? Roughly logarithmic, right, logarithmic log to the base of it is a very small number, we are only throwing away what's 1 by 25th fraction that is guaranteed to be thrown away. So, it will be log to the base of okay, all right, okay. So, let us call it some g of k, okay, where k is roughly log to the base no, not log to the base 25. It has to be a very small number, right?
Alpha fraction
right. Okay. So, 1 over 1 minus alpha, right, whatever that number is. This is very small number because alpha is 0.9, alpha is whatever 0.9 or something. So, it will be no sorry 0.04, right, or something like that 0.04. Okay. So, but still it is which is order, we can still use big O notation saying that it is order log n. So, in logarithmic number of phases we are done with this process. Okay. Eventually, the graph becomes small enough, okay, or essentially graph, let us say GK is a very small size graph. We can stop, let us say, when there are 10 vertices or some such thing, let us say 10 vertices. We can stop at that point, okay. Because once your problem size becomes constant, okay, you can apply any kind of brute force method to solve the problem. Okay. So, we do not go any further. So, G naught to G1 to G2 all the way to Gk, these are graphs that we obtain by eliminating some vertices from the previous graph. Okay. So, there is clearly some kind of, so these are sub graphs of the previous graph. But what is that we are trying to solve? We are trying to actually solve, build a data structure for the point location problem, right. So, initially we assume that G naught is a triangulated graph. If G naught is not triangulated, we triangulate it. Now, we do not know at this point how to triangulate quickly. You know that all planar graphs are can be triangulated, planar subdivisions, because each subdivision is a simple polygon, and a simple polygon can be triangulated. That is something that we kind of proved in the first couple of lectures, right. But we did not quite go through the analysis carefully, and it did not seem like a very efficient algorithm, but certainly it can be triangulated, right. So, each subdivision which is a simple polygon can be triangulated. So, we can assume that either G naught was triangulated, or if necessary we will triangulate it. Right. When we throw away some vertices, okay, and so what happens is, suppose there was this okay, so there was some triangulated graph. So, and we eliminated, let us say, this vertex. Okay. So, if we eliminate a vertex, we are not going to eliminate any of the neighbors. That is the definition of the independent set. Okay. So, we could have eliminated this, okay, and we could have eliminated, well, this looks like a high degree. So, we are not going to eliminate that, but something else maybe let me make the diagram a little bigger. Okay. So, suppose we had eliminated this. Okay. So, once we eliminate this, this vertex is gone. Right. Now, once that vertex disappears, I would like to again retriangulate the graph. Right. So, how do you retriangulate? So, we can retriangulate in many ways, and at this point actually it does not matter what algorithm we are using to retriangulate, because the vertex that we threw out has what kind of degree? The degree less than 12, some kind of constant degree, right. Now, even if we use the most inefficient algorithm for triangulation, it does not matter, because we are dealing with a simple polygon of size at most 12. Right. So, we can retriangulate using any method that you want, right? Practically it will take some constant time. So, suppose this was retriangulated like this. Okay. So, now you can probably see the significance why we did not choose neighboring vertices, because that made this retriangulation process much easier. If two vertices, neighboring vertices were to disappear, then I could not invoke such a simple retriangulation mechanism, right. So, once a vertex is eliminated, okay, so we have to deal only with a simple polygon of size at most 12. This wouldn't have been the case if we had two adjacent vertices to deal with, right. Now, what was the original triangulation? We had a vertex somewhere here, right. Let me throw it back.
But here the independent set has about alpha n vertices, right. So,
yeah.
Each of the triangulation will equal constant amount of work,
right.
But alpha times n of that,
right. Each triangle is constant amount of work, and therefore, the total work that we will be doing is linear in the number of vertices.
Right.
Yes, at each iteration we will do that. So, we'll do the analysis, but for a single vertex that disappears, we are only spending constant amount of time to retriangulate. So, if a constant fraction of vertices are disappearing, then we are spending linear amount of time, linear in the number of vertices, right. That is important. Okay. So, the blue ones, the blue triangles are the new triangles, the red ones are the old triangles. So, how does the actual point location work? The point location actually works in the reverse direction. So, when we only have suppose we have inductively okay. So, consider the last one GK. Okay. So, this graph only has a constant number of vertices. Okay. I can use whatever algorithm that I want to do my point location there. Okay. So, I have, let us say I have done my point location. So, when doing the point location, I am going to actually look at this entire hierarchy in the reverse fashion, okay, for the point location. My first step is for point location. We can do it in, let us say, some constant time in G sub k using whatever algorithm, using some brute force, let us say. Okay. Now, having located in GK, okay, we want to refine the point location with respect to GK minus 1, okay. And then having located the point in the subdivision of GK minus 1, we want to proceed backwards and do the point location, refine the point location in GK minus 2, and eventually we are going to do the point location all the way to G naught, which was the original planar subdivision, then we will be done. Okay. So, what is the cost of refinement? Cost of refinement, I locating in G I minus 1 given location in G I. So, so suppose I have this point, this is my point, okay, and I know that the point is located. So, the blue ones basically means that it's the next subdivision that I have obtained by throwing away vertices, and when I am doing the point location, I am doing the reverse direction, that is I know the point with respect to location with respect to blue, with respect to the blue triangle, blue lines, blue subdivision, let us say, right. So, I know that there are these 1, 2, 3 triangles with respect to the blue subdivision, right. And I now want to somehow know what is the point location when we consider the triangulation defined by the red edges. Okay. And how do we do that? Yes, tree structure, but what is the sort of the easy way, at least to to justify that it can be done easily?
So, means one triangle when it is you have to see now in the refined triangulation what are the triangles that is intersecting that.
Exactly, yeah, right. So, you consider these 1, 2, 3 triangles, okay. These are the triangles of the blue triangulation. Then I can also number the triangles of the red triangulation. Let us say, okay, let me call it, use A, B, C, D, E, F, right. So, if you sorry, what is it? I have missed one edge of the red triangle, right. So, you see there are these A, B, C, D, E, F in the red triangulation, and there are these 1, 2, 3 triangles in the blue triangulation, and all we need to know is how these triangles interact with each other, right. So, let us say triangle 1 intersects triangle A of the red triangulation and triangle B of the red triangulation, right. I am just talking about this particular portion. This is a blue triangle. So, this blue triangle intersects A and B. Right. So, if I can somehow store this information that here is, let us say, a triangle of G I, this is a triangle of G I, okay. I was using blue, so let us use blue. Okay. So, this is a triangle of the blue triangulation, okay, and there are a number of triangles of the red triangulation, right. So, here are my right 1, 2, 3, the 3 of these triangles. Okay, I am not drawing the entire picture, only for that particular subdivision, and there are these A, B, C, D, E, F, right. So, 2, 3, 4, 5, 6, A, B, C, D, E, F. These are these nodes or whatever, these represent the 6 triangles of the red triangulation of that particular subdivision. And what we noticed is that triangle 1, the blue triangle, intersects A and B. So, I will just draw an edge between 1 and A and B. Okay. Likewise, 2 intersects. So, 2 intersects A, B, C, D, and all of them, okay, except E, right. Okay. So, 2 intersects B, C, D, F, okay, and 3 intersects F and D. No, E is not a part of that, right. I mean, that E was never a part of that. So, I should probably never have drawn E actually in the first place. Anyway, that does not matter. So, D and F, right. In fact, this is a spurious triangle. I mean, it is not a triangle that has come from that particular subdivision. So, we have this kind of a structure, and if we know that the point appears in the triangle 3 of G I. So, the point is in triangle 3 of the G I, the only possibilities are D and F, right. So, I will just again using brute force I can check whether it intersects D or F, right. In fact, whatever the case may be, none of these nodes in level I, okay, will intersect more than, or not intersect, I mean we do not have more than, what is the degree of each node basically? 12 at most, right, because there can be at most that's the good thing about the degree bound, right, because when we threw out a vertex, this vertex we created a maximum of whatever was the degree of the vertex, and if this, since the degree was 12, we cannot have a situation where a blue node will have more than 12 neighbors in the level of G I minus 1, right. And this is true. So, when you complete this graph basically, or this is actually has a layered graph structure. Okay. So, this corresponds to G I, then G I minus 1, and then likewise there will be some triangles corresponding to G I minus 2, etc., and eventually all the way up to G naught. And a point location will just proceed starting from somewhere along this layered graph till we hit a triangle in the original planar subdivision, right. And every time when we descend by one level, what is the kind of extra operations of work that we have to do? We have to only check with respect to, if we are here, we have to check all the connected neighbors of that node, and there are at most 12 neighbors of that node. Okay. And each of these polygons is a triangle. Okay. So, if you can figure out, well, whether it is a triangle or rectangle, it is a constant number of sides. So, in constant time we can determine whether the point is inside the triangle or outside the triangle. Okay. So, we are spending constant time to refine our search from level G I to G I minus 1. Okay. And we already noticed that the total number of levels, okay, is order log n, right. So, that immediately gives us a query time of order log n. Point location query time is order log n, right. The order log n, we will do that, but construction time will be counted separately, right. We parameterize three things, right, query time, pre-processing time, and pre-processing and the space. Okay. So, the query time is number of levels times order 1, and since the number of levels is order log n, so the whole thing is order log n. Okay. Okay. Next, let us look at what is the pre-processing time and space. Okay. Okay. So, what are we doing? We are, what is the algorithm? So, if you do not count the cost for the initial triangulation, okay, so that we leave that aside and we will take it up when we actually look at triangulation, the problem of triangulation. So, suppose initially the graph was triangulated. After that, what is the kind of work that we are doing? You are essentially identifying a fractional independent set. How are you doing it? You are finding out. So, I am going to visit every vertex and basically just see whether it has a degree less than 12 or not, linear time, right. Then when I find the fractional independent set, I do it greedily. Again, I am dealing only with vertices of degree less than or equal to 12. So, I can run this entire greedy thing in time proportional to the number of vertices, right. So, at every level, okay, and then of course, I have to also make sure that I construct this search. Well, this is not quite a tree, okay, it is a leveled graph. Okay. So, we should not call it a search tree, it is a search leveled graph. Okay. The edges go between consecutive levels only, right. So, we also have to, we must also construct this search graph, okay, when we are doing the pre-processing, right. But then again, when you take out a vertex, it is only creating a subdivision of size 12. So, the new triangles and the old triangles, they are all bounded by constant. Okay. So, again, even if you use brute force, okay, just to find out which nodes interact with which nodes in the previous level, that is again a constant amount of time, right, because you are always dealing with some constant. That is why we chose this constant degree vertices, right. Just to recap, see, in this red triangulation, what are we doing? We are creating some new triangles and there are some old triangles, okay, and we are finding out the interaction between these sets of two triangles, these two sets of triangles, okay, but there are constant number of triangles that we are dealing with, Okay. The number of red triangles is no more than 12, the number of blue triangles is no more than 12, and therefore we are done.
So, one question, a triangle can survive multiple levels, right? And so, why you are saying that the edges will go only between consecutive levels? They can be that from 2 levels down also different, right?
Yes, what you are saying is correct, but conceptually we can view all the triangles that, let us say, survive to actually move up.
So, you duplicate that thing also?
Yeah, we can duplicate that. Yeah. So, what you're saying is correct, that some triangles can survive, but just to simplify conceptually, we are we consider a triangle that has survived, make a copy of the triangle to the next level, right? And we do not lose anything asymptotically, but of course, when you are probably implementing, you may not want to do that. I agree with you. Okay. It's a good point. So constructing this search graph as we go on eliminating the vertices will also take us time proportional to the number of vertices in that particular level, right. So, time at level I, okay, is basically order of Vi. Vi is the number of vertices in level I. Because they are planar graphs, the number of edges is proportional to the number of vertices and so on and so forth. Okay. So, therefore, total time, pre-processing time, right, okay, and we know that Vi is less than or equal to alpha times right. No, but even if you duplicate vertices, what is the total number of triangles? Number of faces. Number of faces is always proportional to the number of vertices in a planar graph. Your total cost is always going to be proportional to the number of vertices. It will be multiplied by some constant. Yeah. So yeah, this way I can, in fact, this actually simplifies analysis. Otherwise, you will be worried about what is duplicated and what is not duplicated, right. So, at every level, the vertices is a constant fraction less than the previous level. The total work that we do is proportional to the number of vertices, because edges and faces are all proportional to the number of vertices. So everything becomes basically proportional to the number of vertices, and since this is a constant fraction, this is just a geometric series, which basically nothing but order of . How much is the space? Each vertex of the search graph has constant degree, right. We do not need to count those edges. Okay. So, again it will be proportional to the number of vertices in each level, and again the number of vertices in each level correspond to the number of faces in each level, right. And again by this previous argument, so space is proportional to summation of number of faces in each level and number of faces in each level is again proportional to the number of vertices. So, they will also be decreasing by a constant factor. So, overall then again it is going to be order V. So, the search graph is the structure that is the data structure essentially. That is the data structure, and this is the size of the data structure. The data structure is also bounded by something that is linear. Of course, this alpha, okay, the smaller it is, the better, in the sense that everything is hidden inside this constant, right, subsumed by this big O notation. So, if alpha is close to 1, okay, the constant here is going to be larger, right. It is 1 over 1 minus alpha, and if alpha is smaller, then the constant is also going to be smaller. If you can get a larger reduction, your constant. So, and the constant that will show up here is very large, alpha is like, what we have noticed is very close to 1, 0.9, 0.95, something like that. So, this constant could be like about 25, 30 or something like that, which is not such a nice thing. Okay. So, when one has to implement this, one should use, as I said, we do not need to actually duplicate the nodes, etc. And even this bound that we obtain, that is 1 over 25, is a kind of a loose bound, it can be tightened. And moreover, when you actually, if you actually were to implement this in practice, which actually by the way people do not. The reason why this algorithm is very significant is not simply because it is elegant and conceptually simple, but it also leads to it gives you a method where when we have a planar subdivision or planar structure, it gives like a hierarchy of the planar structure. Okay, and this is not only useful for point location, but in some other problems as well. Okay. So, one byproduct of this algorithm. So, by the way, this goes under the name of Kirkpatrick's algorithm. Okay. So, a byproduct is the hierarchy of the planar subdivision. Okay. And this it basically starts, if you go bottom up, look at the GK, that is the most coarse subdivision. Okay. And then you get a slightly more refined subdivision and so on and so forth. So, it basically gives you a, so if you did not want, let us say, in many applications in graphics, etc., you may not want the details of the surface in certain applications, but you may, it is like this, the closer you get to a surface, the more details kind of shows up. Okay. So, this kind of hierarchy is used all the time for visualization. So, especially if you are in a moving body, you are moving towards a scene. Okay. As you come closer to a scene, you see more and more details, and one way that it can be implemented basically is that you have a triangulation of the surface. Okay. And if you can store a hierarchy of these triangulations, okay, that gives you this effect that as you move closer, okay, you see more and more details of it. Okay. So, that is one application. Another application is that so we have already observed that a 3-dimensional polytope, okay, also has the structure of a planar graph, right, and that is the reason why the 3-dimensional polytope is also has number of faces, a number of vertices, number of corner points, all proportional to each other. Now, if I pose the problem that we posed in 2 dimensions, that is, I give you a convex polytope and I give you a plane and ask you which is the corner point of the polytope nearest to this plane. So, in 2 dimensions we could solve this problem, or at least I gave it as an exercise to solve this problem in log n time using some kind of binary search, right, some variation of binary search. If I give you a convex polygon and a line, you report either the line intersects, okay, or find the point in the the corner in the convex polygon which is closest to the line. Now, the analogous problem in the 3 dimension is I give you a convex polytope in 3 dimension and a parametric equation of a plane, and again you tell me the same thing, does this intersect or whatever, find me the nearest corner point of that polytope to this plane. Right. So, that problem can be very nicely solved using this hierarchy of subdivisions, okay, and it can actually be solved in logarithmic time. So, even in 3 dimensions we can do it, and it is because of this kind of a subdivision. So, the Kirkpatrick's decomposition has many other applications, but the reason why it sort of it is studied is not because it is important for just 2-dimensional planar point location, but it has other kinds of application. It is a very nice, it is a very conceptually simple way of generating a hierarchy of the planar subdivision structure. Right. And as I said, to the contrary, because it is high constants, people do not use this in practice for planar point location. what is used for planar point location is something that I will take up next, and that will go hand in hand with what I postponed just a moment ago, that is triangulation. Okay. How do we triangulate a simple polygon? Okay. In fact, we will take up a more general problem. So, if you do not have any questions, we will move forward. Any questions with regards to this?
What is the corresponding thing to triangulation here and you said the polytope and plane? So, here there is no triangulation, right?
No, you will triangulate. So, say a convex polytope. Well, you generate what is called tetrahedrons.
Okay, so you got the
So, triangulation higher dimensions basically is the simplex, the simplicial decomposition of that body. Okay. So,
the algorithm is similar to this, right? They are also
the algorithm will be very similar to this in the sense that you are going to generate. So, this convex polytope, which is the original convex polytope, can now you basically throw away vertices, it becomes a simpler polytope. You throw away more vertices, it becomes a simpler polytope. Okay. And then when you do this, try to find the nearest vertex, you can there is some neighborhood property that you can So, you look at the simplest, or let us say the bottommost in the hierarchy is a convex polytope. Let us say it is a constant number of vertices. Okay. And then you can find by brute force the closest corner point. Now, you throw in some more vertices that were eliminated in the structure. Okay. Then you can kind of prove that whatever is the nearest point in the present hierarchy, okay, as you throw more points in, the nearest point will be one of the neighbors of these point. That follows from essentially the hierarchy, the Kirkpatrick's decomposition. Okay. So, it is a very clever algorithm, and not only that, you can also determine the closest neighbors of two convex polytopes using this method. Not just convex polytope and a plane, but I give you two convex polytopes. Find me the closest pair of vertices of that. So, that can also be done using this method. Okay. So let us talk a little bit about triangulation. Now, triangulation of simple polygons is what that seems like a very important problem, but it is not just triangulation of simple polygons. Triangulation can occur in other contexts also. Okay. So, I can give you just a set of points and ask you to add edges between pairs of points, okay, so that each face becomes a triangle. Can you always triangulate a set of points? Is it always possible? We talked about triangulating a simple polygon. Here I am just talking about a set of points. I mean, these are points on the plane. Yeah. So, what is a quick justification of that?
So, maybe I can take the convex hull of the set of points and then triangulate it?
Yeah, sure. So, I should actually define it properly. So, what you are saying is correct, that so when you talk about triangulation of a given set of points, you can well, it is not necessary, but you can think about it like you construct the convex hull of the set of points, okay, but there are points inside. It is not enough to just construct the convex hull, but what we can say is that we can limit ourselves, okay, we can limit ourselves to triangulating basically this boundary. I will not bother about so the outer face, okay, I can sort of ignore at this point. So, let us say that we are only interested in triangulating all the points inside the convex hull.
So, you can triangulate 3 points, for example, and if you have another point anywhere, you can always show that you can have.
Okay. So, what you are saying that suggesting is the following. Right now, I have a set of points. Okay. I take any 3 points. Suppose I take this point, and this point. Okay. I triangulate. Okay. Right. No. So, I triangulate. I notice, and suppose there is a point inside, or there is more than one point inside. Okay. I add this. Okay. There can be more points inside. Okay. I can keep doing that, and that is essentially a proof that everything can be triangulated. Good. But there are, so one thing to notice is that triangulation is not unique. Okay, there can be many ways that you can triangulate a set of points, and for certain applications certain kind of triangulations become important. Okay, and one very important kind of triangulation that we will learn very soon is called the Delaunay triangulation. Okay, but there are other kind of triangulation that where these are all mostly used for surface modeling purposes. This is very important. Okay, so we can triangulate any given set of points. Actually, the problem of triangulating a simple polygon is harder. Why? Because we have to also be conscious about that we should not cross any edges of the simple polygon, right. So, it is called a constrained triangulation. So, if you are just given the points of these, suppose we are only given these points, okay, that is not the same as triangulating a simple polygon through this, right, because now I have to make sure that when I draw this triangle, okay, we should not intersect the simple polygon itself. So, this is called constrained triangulation, and in fact, it can be even more general, where it need not be a simple polygon, but a polygon with holes inside. Okay. So, we can have a situation where you can say that this is the outer simple polygon or something, but I could also have some structure inside. Okay. So forth. So, again when I triangulate, I must make sure that the edges that I introduce for triangulation do not intersect the original edges. So, we will actually take up this more general case for triangulation, right. And we will actually treat this given whatever this polygon with holes as essentially a set of non-intersecting line segments. Yeah.
So, you said that there can be many triangulations. So, each triangulation has same size, or I mean they are roughly same size, or
oh, you mean in terms of number of faces? So all these triangulation have fixed number of vertices, right. So, we will actually now look at the problem of this one, we will check out the more general case, okay, and input is, let us say, we can think about the input as essentially a set of line segments. Which question?
So, when we are triangulating a polygon, are we introducing points in the interior?
No. So, we are not introducing any Steiner points, that is the question, right. We are not allowed to introduce Steiner points. So, triangulation,
corner points will be,
yeah, only the corner points can be used. Okay. So, maybe I should say no Steiner points. Okay. So, I guess what the question is this, are we allowed to triangulate like this? So, here we are basically introducing these Steiner points. So, we are not allowed to use Steiner points. When you talk about triangulation in the context of simple polygon or computational geometry, we are not using any Steiner points.
But in vertex polygon, at least simple polygon, that has at least exactly n-2 triangles, right? I mean the triangle.
Exactly.
But I don't know, is it true also for general polygons also? Or?
General polygons as in?
Kind of holes and etc.
Yeah, I should be able to prove that too.
there are no extra points in it.
Okay. So, n-2 for faces. I mean,
Well, I mean, why don't you compute that? So, see, you can triangulate the interior of these things, right, and so you just look at the entire triangles and then subtract the number of interior triangles. So, everything is fixed, right. So, number of triangles inside will be fixed, right, and the outer number of triangles will be fixed. So, the total number of triangles should be fixed, right. So, input is given in terms of line segments, and we would like to introduce edges, some kind of edges to triangulate this whole thing. Right. All right. So, this is we will take up this problem tomorrow, and we will actually establish a nice reduction between the ray shooting problem and the triangulation problem. Right? But before that, I will just leave you with this, just to think about it. Suppose my triangle was very very simple, in the sense that it looked like it's like this. We have one edge, okay, and we have a monotone edge, a monotone polygonal chain on this edge. Suppose we are to deal only with this situation. So, I leave you with this to think about whether this particular case can be handled easily. Are you with me? There is only one base edge, okay, and there is a monotone polygonal chain. Of course, simple polygons being anything but simple, crooked, very curvaceous simple polygons, you can't deal with, but this is a very nice structure. So, can you deal with this situation very easily? Something for you to think about. Okay, stop here.